first of all, thanks for letting me do this presentation online. I'm really sorry I can't be there, and I apologize in advance if I'm a bit slow. It's really early in Germany, but I hope I make everything clear. So my talk is called Start Making Sense, Understanding Particle Physics with Deep Neural Networks and Explainable AI. And to give you an idea what I want to talk about, I will give you a short introduction. Okay, does it work? Okay, yeah. So you have probably all heard about the discovery of the Higgs boson in 2012, which made worldwide headlines. But how exactly this particle was discovered at the time and what this diagram here has to do with it is probably lesser known, so I will quickly talk about that. So what they did at the CERN and the Large Hadron Collider is they accelerate protons to very, very high energies, and then they let them collide. And then in the scattering products of this collision, physicists search for new particles. The problem with this is that events where new particles like the Higgs boson are created are extremely rare. And also these particles rapidly decay into other particles. So the particles that are actually measured are not the Higgs, but decay products of it. And so to identify the Higgs boson, one thing that physicists did was to reconstruct the intermediate particle masses. So the masses of the particles that were somewhere in the collision. And then they plotted that against the frequency of those events. And this is what you can see in the diagram here. And now, without a new particle, they expect this smooth distribution of this red dotted line. However, if there should be some kind of new particle, they expect a sort of bump, which you can see. I just try to use the pointer, which you can see here. And so this bump is kind of an excess of events at a certain mass, and this signals that there could be a new particle. And they then analyze whether the properties of these events aligned with those that were predicted for the Higgs, and they did, and so they claim to have made a discovery. But now imagine you're only being told the classification. So there is something new, which is different to what we have known so far about physics. But without understanding anything about what I just talked about, the mass, the different particles, and so on, and you do not really know how this classification was reached, or not a lot about the underlying physics. And that exemplifies a key role of deep neural networks in particle physics, which give you quite accurate predictions, but little to no understanding about the physics behind it. And as physicists aim to understand nature, the question I want to talk about today is, can we truly understand particle physics with deep neural networks? And the plan for that is that I'll start by talking about scientific understanding. We'll then talk about understanding in particle physics. So what do particle physicists do to understand? I will then show you how DNNs pose a problem to that. And I will then talk about understanding with deep neural networks. So let's start with scientific understanding. So there are a lot of philosophical theories about scientific understanding. There are quite famous ones by Khalifa, by Dirac, by Elgin, Strauss, and so on. And they all disagree in a lot of ways. And therefore, what I did is to find minimal conditions for understanding. So conditions that have to be at least fulfilled to talk about understanding, and conditions that all of those theories seem to kind of agree on. And the first condition for that is the minimal effectivity condition, which says that understanding should at least answer to relevant empirical facts. The next condition is the achievement condition that says that understanding is valuable because it can lead to the achievement of further epistemic and in turn practical ends. And the last is the minimal abilities condition. So this says that grasping is necessary for understanding, and this grasping requires an agent to at least have a mental representation of a phenomenon or subject matter, which equips one with being able to give answers to what-if questions concerning that phenomenon or subject matter that were not already known. But keep in mind, this is a minimal view, so stronger conditions for this are possible. And those stronger conditions then give rise to different kinds of understanding. So for example, Catherine Elgin's view on understanding does have this minimal effectivity condition, but she has really stronger condition on the abilities. And the understanding I want to talk about today is explanatory understanding with. And that is the understanding described by Morrison and Morgan and Henk de Recht. And here scientific explanation is typically model-based. So a model represents a phenomenon such that a theory can be applied to it. And as there are no algorithms or rules for model building, it is based on scientists' skills and pragmatic decisions. And therefore, if a scientist wants to explain a phenomenon on the basis of a theory, she needs skills to use a theory for model construction. And importantly for this kind of understanding is that the theory needs to be intelligible to the scientists. Now, what is intelligibility? De Recht argues that a scientific theory T is intelligible for scientists if they can recognize qualitatively characteristic consequences of the theory T without performing exact calculations. So intelligibility is the value that scientists attribute to the cluster of qualities of a theory that facilitates its use. And such qualities are, for example, visualizability or simplicity. And what you then gain from that is to get a feeling of systems behave. So for example, with the depiction of field lines, you get a feeling of how electrostatic systems behave, and that is what it means to have an understanding of the situation according to this kind of understanding. Now, the question is, how do the conditions for explanatory understanding with diverge from the minimal conditions? So for the factivity condition, we have that explanatory understanding with should at least answer to empirical facts, but does not require correspondence with unobservable elements. So instead, it is more important that the theory or model is intelligible. Therefore, we have intelligibility over truth. And for the abilities condition, explanatory understanding with requires grasping a representation, which is an intelligible theory or model, which requires the ability to reason qualitatively and use the theory or the model to construct explanations. And therefore, to kind of sum up what I said about scientific understanding, understanding should at least answer or satisfy the minimal effectivity condition, the achievements condition, and the minimal abilities condition. And higher levels of understanding might imply more constraints. For example, for explanatory understanding with, we have that models are essential for scientific understanding, intelligible theories are required, and we have that visualizability and other qualities serve as tools for understanding. And with that, I come to the second part, which is understanding in particle physics. So to understand particle interactions, for example, at the Large Hadron Collider or just in general, physicists have the standard model of particle physics, which describes how particles interact. And it is a model that describes the fundamental forces in the universe and classifies all known elementary particles. And as you can read on the website of the CERN, it says the standard model explains how the basic building blocks of matter interact, governed by 4 fundamental forces. Now, one part of this model is called quantum chromodynamics, or QCD for short. And this part of the model explains how quarks interact. And quarks are the particles protons are made of. And the problem here is that the predictions of QCD are very good at very high energies, but there seem to be no reliable calculations of complex phenomena at lower energies. And therefore, to understand what happens at these lower energies, physicists use quantum chromodynamics inspired phenomenological models like the string model you can see in the picture here to comprehend specific features of quantum chromodynamics. So for example, one thing that happens at lower energies is that particles come together and hadronize, so form multi-quark particles. And this is what the string model is trying to kind of visualize, because it visualizes the formation of hadrons at low energies, and is the visualization of the color field between a quark and an antiquark as collapsed into a flux tube that, somewhat like a rubber band, absorbs the increasing energy until it tears. and this tearing corresponds to the creation of two quark hadrons. And as this is a bit abstract, here's a short animation of that. So you have a quark and an antiquark, and when it's connected by this flux or gluon tube, and when the energy increases, it tears. And when it tears, you have those two quark hadrons. Now, the question is, what is the difference between a model like the standard model of particle physics and this string model? Well, the difference is that the standard model is an explanatory model, and it is grounded in fundamental theoretical work and does not just describe what happens in particle interactions, it explains why particles interact the way they do due to the forces and so on that the model describes. The string model, on the other hand, is a phenomenological model, which describes what happens, but not why on a deeper level. So it lacks insight into the mechanics that produce the phenomenon. So it is not explanatory and instead answers a descriptive what question. And a second thing that goes on with these phenomenological models is that understanding with them comes with a loss of meaning. So what do I mean with this? Traditional models in physics or in general normally have physical meanings for mathematical symbols. And phenomenological models in physics, however, are connected to but not derived from theories, and they're connected to observed data via free fittable parameters. And the problem with these parameters is, as Hasse and Lennart have analyzed, that these models do have parameters which describe physical quantities in the simple context for which they were initially developed, but in the complex context in which they're used as fitting parameters, the original physical meaning is lost. And so, in a way, the parameters are not meaningful and are not used to represent specific features of the target system. And of course, with this comes the question, can we use phenomenological models for understanding? And moreover, why do physicists even use them? And one answer has been given by Stefan Hartmann, who said that besides providing useful calculations and predictions, physicists value such models not least for their ability to provide plausible qualitative stories that aid understanding. And they are constructed by means of visualization that allow to make qualitative predictions without carrying out calculations. So the animation, for example, I showed you depicts this underlying physical intuition of the modeling process. And this sounds a lot like the understanding Direct talks about. And indeed, this has been picked up by Direct, who showed that these models are hence intelligible to working scientists and thereby provide a basis for advancing our understanding of quantum chromodynamics. And as we saw for explanatory understanding with, we need intelligibility. And the string model does indeed do that. It makes quantum chromodynamics intelligible because the model is constructed by means of visualizations of hadrons that allow physicists to make qualitative predictions about their structure without carrying out calculations. And so the visualization of this model here is a tool for understanding with this model. And so to kind of wrap up what I said about understanding in particle physics, what we have established until now is that in particle physics, traditional models and phenomenological models are used to understand something. However, traditional models are explanatory deeper. Both of them, however, serve, among other things, as visualizable aids to make complex theories more intelligible. And so for understanding with, we need this intelligibility. And the problem now is that the use of deep neural networks disrupts this visual interpretability. And with that, we come to the third part, the problem of deep neural networks for understanding. So to what extent and how do deep neural networks hinder the understanding of particle physics? So as you probably all know, deep neural networks act as opaque mappings. So they solely translate some inputs to outputs, and they're essentially black boxes. And we do not know how a DNN reaches a certain prediction. So what exactly happens between the input and the output is unknown to us. This is, for example, captured in the following quote by Seiler et al., who say that large convolutional network models have recently demonstrated impressive classification performance. However, there's no clear understanding of why they perform so well or how they might be improved. And coming from a physicist side, Physicists like Shang et al. Have been saying that a common argument against using machine learning for physical applications is that they function as a black box, send in some data and out comes a number. While this kind of non-parametric estimation can be extremely useful, a physicist often wants to understand the underlying physics. So this lack of understanding prompts kind of an updated spectrum of understanding with models. So as I said, there's this gradual loss of meaning from ordinary models to phenomenological models, but the latter are still based on some theoretical elements and they provide us with qualitative predictions. So in a way, they still offer some kind of understanding and we at least grasp what the model is trying to represent. Now, with deep neural networks, there's this total loss of this total lack of grasping of what is being modeled, which leads to a loss of physical intuition that is present with phenomenological models. Because the parameters in deep neural networks, such as weights and biases, lack specific meaning beyond their role in training and adjusting the model. So we do not even know what they represent about the target system. And we do not have visualizability or other qualities that make it intelligible as we had with normal models and phenomenological models. And so what seems to be at issue here is that while DNNs seem to provide scientists with highly accurate predictions, they leave the underlying physics and how they have reached their results mostly unintelligible. And so in that sense, it seems like we do not get explanatory or deep understanding with DNNs, and also not the understanding we could gain from phenomenological models. So we do not even know what happens and definitely not why. And therefore, the question is, can we use deep neural networks to get understanding? And this has been debated a bit in the literature already, so where different philosophers have kind of analyzed what it is that keeps DNNs from giving us understanding and what could be a possible bridge to understanding. So, for example, Emily Sullivan has said that it is not DNN's black box nature that inhibits scientific understanding, but the degree to which they contain link uncertainty, and that is a lack of scientific and empirical evidence supporting the link that connects the model to the target phenomenon. So for her, a bridge to understanding would be link certainty. Retz and Weisbart have countered that only weak objectual understanding can be gained from deep neural networks, and deriving actual explanations from deep neural networks prediction would require a much deeper insight into the inner workings. So a bridge to understanding here would be to have XRI methods that illuminate the inner workings of a deep neural network. And Florian has said that C instrumentality, so instrumentality qua devoid of content, and what opacity threatens scientific understanding. And for him, therefore, a bridge to understanding could be XRI methods that target what questions. I will come to that in a minute, but let's first talk about explainable artificial intelligence, even though I'm sure you all know what that is. They are just systems designed to provide understandable explanations of machine learning processes and decisions to human users. And an interesting thing about them is that many of them correspond to or give rise to visualizations or other qualities, as well as qualitative predictions. The problem now is that we can use XRI methods to gain at least two kinds of understanding, as Sullivan has argued. One of them is the understanding of the machine learning model, and the other is the understanding of a phenomenon with a machine learning model as a vehicle for understanding. And as scientific application often focus on understanding the underlying mechanisms that give rise to observed patterns in the data, it seems to be the latter that physicists are mostly interested in. Because understanding only how the model works is not sufficient for understanding the relevant subject matter. For that, it is also important to understand what a model says about the relevant domain. And this is exactly what is captured in the two dimensions of opacity, the how and what opacity, where the how opacity deals with questions of the details of how a certain DNN arrives at predictions, and what opacity with questions on what the DNN learned about the subject matter. So when we only understand how a model works, we still have no grasp on what is in the data that drives this process. And to give you kind of intuition of what the difference between how and what opacity is, just imagine that a meteorologist is telling you, I'm really sure that it is going to rain tomorrow. and you are an aspiring meteorologist and you want to understand why that is the case. And so your first idea would be to go via this how path and ask, how does the meteorologist's brain work? And maybe you learn which regions and neurons are activated when making the predictions. And maybe you learn how the learning process works. But then you think about it and you kind of think, okay, I didn't really get an understanding of why it is going to rain tomorrow. I just learned how his brain works. And so your second idea is to just ask the meteorologist what made her reach this decision. And for example, you could learn that there's a low pressure system that comes into the area and brings clouds with it. And maybe you are also being told that this is a crucial point for the prediction of whether it is going to rain tomorrow. And then thinking about it, this is a kind of first step to understanding of why it is going to rain, because you can connect this now to background knowledge, you can start modeling, and so on. So this is a first step. And so coming back to the spectrum, traditional models can help us understand why something is the case, while phenomenological models can at least give us an understanding of what is happening. Now, both are connected to the target and give us grasp of what is being modeled. But DNNs lack this connection to the target, which results in a loss of meaning and uncertainty about what is being modeled. And models that we want to use for understanding natural phenomena should contain rich enough representations to make the mechanisms intelligible. And what I showed you until now is DNNs alone cannot provide such rich representations for understanding mechanisms. But the hope with these what methods is that XRI methods can maybe build a bridge to understanding by providing exactly that, representations that in the best case help us conceptualize some underlying mechanisms by making the DNN intelligible. And therefore, that gives us a grasp on what the DNN represents and a deeper connection to the target. So the hope is that XRI methods can bring us kind of more onto the green side of the spectrum of understanding with. And when we look back on our conditions for explanatory understanding with, kind of springs to mind that it is exactly this intelligibility which is missing for understanding. And now in the remainder of the talk, I want to talk or kind of analyze how much understanding and in what way we can get understanding with deep neural networks. And the first case study I want to look at is called data planing. This is an XRI method that is used on a deep neural network that classifies events as signal and background, so as kind of something new and known physics. And here in the upper left picture, you can see kind of visualized how a classifier was able to detect a signal, which is the green line, and the green line is a blue, the end of the red line is a green line, so there are kind of two new particles. And you can see how it was able to detect the signal, the red line and the green line, and this can be distinguished from the background, which is the blue line. And you can also see that there's this bump now, which signals that there could be a new particle, just as I showed you in the beginning for the Higgs boson. And what they did now is they removed the information of the reconstructed mass from the data. So remember in the beginning, I told you that this mass information was what made physicists find out that there could be a new particle. And now you can see in the picture below, so in this one, you can see the planed data. So the data where the reconstructed mass has been removed. And you can see that the signal and the background now have identical distributions. And the interesting thing is now that when they trained the network only on this data, on this planed data, the network failed to distinguish the signal from the background. And so the DNN lost its ability to discriminate. And in that sense, the reconstructed mass, this variable, was a discriminating factor, and the deep neural network used that variable. But now, what do we understand with data planning about particle physics? So through the histogram I just showed you, we learned what hidden pieces of information in the data drive the learning process, as the DNN relied on them for the classification task. And this information can be important for the understanding of particle physics, because for one, this high-level variable, which is the mass, and that the DNN used captures physical insight into the data. And in addition, possessing the information about the mass significantly influences the selection of models we could use to make sense of the detected tracks in the data. And moreover, for the green particle, they also found out that there's another discriminating factor, which is something called the rapidity difference. It's not really important to understand what that means, but it is important then that this variable connects to how a particle couples to other standard model particles. And so we gain also qualitative predictions or insights into how the particle we kind of found couples to other particles, which again further limits the selection of models we could use to make sense of the data. And so in a way, with this, we get a first step to understanding something about physics. So we learned what variables are responsible for the difference in signal and background, and we understand qualitatively how new particles couple to other ones. And kind of to go back to our scenario, now you don't have a meteorologist that tells you something, but kind of have a DNN, which output says that I'm really sure that this event is a signal rather than a background. And you as a physicist now want to understand why that is the case. And of course, you can't just ask the DNN just like you did the meteorologist, but you can build an XI method that reveals what made the DNN reach this decision. And you learn about the reconstructed mass, you learn about the rapidity difference, you learn that those are crucial points for the classification of signal versus background. And in that way, you have the first step to understanding that the event, why the event is a signal rather than a background. And the XI here method can be seen as a tool for understanding because it provided visualization and other qualities to the deep neural network. And so now we do have an intelligible representation, and we are also able to reason qualitatively. So those two things we have now for explanatory understanding with. The question is now, are we also able to construct an explanation based on this representation we found, or do we only have a description? And in the data planning case, we are able to use the model to construct an explanation because the information about the mass and the rapidity difference is rich enough to severely limit the models we can use to explain the phenomenon. So they really point us to the explanation that the data must be originating from a certain kind of new particle that interacts with other particles in a certain way. And so in this case, we would also be able to use the theory to construct explanations. But this is, of course, a bit cheap because this is a benchmark study and they used fabricated data where everything about the particle that was kind of found by the DNN was already understood. And they only planned for variables like the mass and the rapidity difference that we already knew and also knew to be important in such cases. So it was already understood that those two variables are discriminating factors for the decision of whether it's signal or background. And so it's a bit like asking the meteorologist what made him reach this decision while already knowing what made him reach this decision. The question now is, what about cases where there's something that we cannot understand or that we do not understand, and in cases where we do not understand as much about the data as we did in the data planning case, so in cases where we lack theoretical understanding. The question is, can we then also gain explanatory understanding with? And the problem here is that, of course, we can search for the mass and the rapidity difference and other variables, but it could be that there are deep representational features that we do not know yet. Like, it's in a sense like before the spin of a particle was known, nobody would have kind of thought to look for that in a deep neural network. And to talk about this, I'm coming to the last part of the talk, which is another case study. This is now in jet substructure classification. And here it's the case that in high energy collisions that we are looking at, jets, which are collimated sprays of particles, are produced. And by analyzing the pattern and distributions of those particles, deep neural networks can classify those jets. And different jets are due to different processes, so they come from different particles and different decay routes. And while DNNs really excel at that, it is far more challenging for humans. So in the image above here, you can see how many jet images of the same type look layered on top of another. So they make distinctions visible. In the picture below, you can see individual jet images where the task becomes much harder as they appear nearly identical. But DNNs excel at this, and they are better than humans in discerning the jets. So there's a performance gap between kind of human methods and a deep neural network doing the classification. And we want to now understand why there is this performance gap, or what makes up for this performance gap. And for that, Fawcett et al. Used an XRM method that is called ADO, that is short for average decision ordering. And they used this method to translate the decision-making process of a deep neural network into a simple set of understandable high-level features that then can be used to make the same classification decision. And for that, they introduced the ADO metric. And this metric does not only compare the overall classification performance, but also the specific classification decisions. So in that way, it measures the degree to which the DNN and the simpler model with the high-level variables make the same classification decisions in the same way. And this works by comparing the network with a simpler network that is only used with high-level variables. And it then works iteratively, so it first identifies the high-level variables that most closely aligns with the neural network's decision, and then seeks additional variables that account for the discrepancies. And this continues until the high-level variables collectively approximate the network's decision as closely as possible. And so what they did here is they first used all the variables that kind of humans would use to classify jets, and then there was this performance gap. And for this performance gap, they used a database of variables that are called energy flow polynomials. And they tested them, and in the end, they found one variable that could account for the performance gap between the deep neural network and the human-generated methods. So the question now is, what are energy flow polynomials, or EFPs for short? So they're tools for analyzing energy patterns in collisions. So they capture patterns in momentum and angular differences and energy flows between particles. And you can see some of them here. The nodes here represent individual calorimeter cells, which are points in space where particles' energy is being measured. And the lines represent the angular relationships between the pairs of cells. And together they capture complex relationships among particles in collision events. Now the question is, what is the difference between using kind of mass, rapidity difference, and so on to kind of translate the decision of the deep neural network, and what is the difference to using EFPs? And what makes a lot of sense to talk about this distinction is the distinction between data, phenomenon, and theory by Bogen and Woodward. So they said that the data represents the immediate observations, such as where particles go and how much energy they carry after collision. So it's kind of what is fed into the deep neural network, the information of the calorimeter cells of the energy that was being tracked in a collision event. And the phenomenon refers to the higher level abstract events we are interested in explaining. So a certain decay route or a certain process that kind of accounts for the data. And the theory kind of explains the phenomenon. So the standard model would, in the best case, explain why the phenomenon occurred. And with this, we can kind of talk about the difference between using EFPs and something like mass and rapidity difference, because mass and rapidity difference are conceptually really rich. So they are easy to embed into theories and background knowledge, and we know what they mean. So they are very close to the phenomenon side. And the EFP is not so easy. So they basically only describe as they are not conceptually rich enough. And it's not as easy to connect them to the phenomenon. And that is the difference. So EFPs are conceptually less rich, so they have less representational depth than higher level variables like the mass or rapidity difference. And so they are more on the data side and describe the data, while mass and rapidity difference do much more relate to the phenomenon we want to understand. So the problem for explanatory understanding with deep neural networks in such cases is that the intelligible representation we gain from this method we just looked at only answers what features in the data does the DNN rely on, or what are characteristics of these events. So it only answers a kind of descriptive what question. It describes the data and does equip one with the ability to classify jets. And it is a first step to explanatory understanding with, but in a way, what we gain here is something like a phenomenological model, because we have only answered kind of what happens and not why. But for explanatory understanding with, we also want to explain why these features emerge. So why does it have these features? And the features we found with the ADO methods are not the underlying mechanisms that we are looking for. While they do give rise to the features in the data, we do not understand the underlying mechanisms until an explanatory model is available. And in a sense, it is always opaque what gives rise to this novel data until an explanatory model is available. And this has nothing to do with deep learning as it is, and is not a question about the model, but about the real world target. And so what is missing for explanatory understanding with is that we cannot use the theory or the model to construct an explanation, as the variables we found are not rich enough for that. To kind of be rich enough, we would have to first kind of interpret the variables so the EFPs in terms of the physical characteristics they present. So the one problem is that these EFPs are not that much analyzed, and there's not so much physicists know about them. But the EFP they found to kind of close the performance gap was analyzed, and they found that the physical feature it captures is the presence of two distinct regions of energy within the jet. And this kind of brings you one step closer. But the important thing is that you then explain these features by embedding them into an explanatory theoretical model. And this, of course, is not easy and requires a lot of theoretical work. But what you want to answer with this is, why are there those two distinct regions of energy? And the answer could be something like, because something decayed into two quarks or whatever, and this should be explained by the standard model or a new model whatsoever. And so unfamiliar patterns here suggest probably something new, like a new force or a new particle, or something we don't even know could exist, like a spin or so on. And therefore, in cases where deeper representational features are not yet known or understood, it can be useful to start by interpreting with shallower features, and those that are closer to the data side and therefore more straightforward. And these features, while they are less mechanistically deep, are often more accessible and provide an initial basis for understanding the data. And so by starting with interpretable and data-aligned representations, scientists can begin building qualitative understanding that is intelligible as a first step to deeper understanding. So it is similar to how phenomenological models allow us some understanding and are used as long as we do not have explanatory models to account for them. And the shallow features can serve as a starting point, enabling researchers to build up to more mechanistic understanding. So they provide an accessible base level of intelligibility. And in the absence of a theoretical model, those shallow features provide an initial framework for understanding how the DNN perceives the data in human understandable terms. And this initial interpretability can maybe act as a springboard, helping researchers identify patterns or relationships that they can then later attempt to explain at a deeper level. And to wrap up, it seems like XRI methods here can serve as a first step to understanding. They can give intelligible representations of the target system. But in cases with limited background knowledge and understanding, starting with a shallower representation can be useful. And those can then be used as a base to construct models and connect the representation to a theory. And so what we learned from this case study is, for one, that DNNs themselves are not capable of generating explanatory understanding with, but XRI methods can provide intelligible representations, and scientists could be able to link the predictions and representations to scientific theories. And so in those cases, to answer an explanatory why question, it is useful to first answer a what question. And the role of XAI here can be best described as a translation rather than an explanation, as it translates the deep neural networks decisions. And finding those unknown whats is a first step to understanding why. And therefore, to conclude, how can we gain understanding in particle physics with deep neural networks, or how can we gain explanatory understanding in particle physics? So in particle physics, XRM methods are needed to explanatory understand a phenomenon with DNNs. And in particular, the right XRM methods are needed. So those that do not deal with the machine learning model's intelligibility itself, but rather with intelligible representations of the target subject. And this intelligibility can be gained, for example, by translating the features the DNN relied on into a human understandable form. However, this only answers what features are characteristic of the phenomenon, and to answer a why question, why it has these features have to be interpreted physically and connected to a theory or matched by an explanatory model. And with that, thank you for your attention. Yeah, my
thanks very much. I've turned on the mic so you can hear the round of applause. Thanks a lot. Any questions? This is Andre Curtis Trudeau.
Thanks for the talk. I kind of had a question about something that you, I guess, didn't talk about. So I get that you're thinking that XAI methods can allow us to recover potentially useful explanatory information from a DNN. I'm wondering if you have any thoughts about a kind of alternative approach to the issue, which is this sort of field of physics-informed machine learning, where, as it were, you're trying to build kind of physically motivated principles and insights into your machine learning system, so that, and I take one of the motivations for this kind of work is that you don't have to go back and try to sort of extract what's in there with an XAI method. Do you have thoughts about whether that kind of approach might help with the sort of stuff you're interested in, or is there work that's trying to do that? Or yeah, what do you think?
I haven't really thought a lot about physics-informed machine learning. So at least not in the way you would do with deep neural networks. Because I have talked to some physicists who kind of used decision trees that are more physics-informed. But yeah, I haven't really kind of looked into this too much because I'm kind of trying to focus on deep neural networks to not kind of have too much I have to look at, but in a sense, I think this would make sense. So those physicists I talked to use those different methods to kind of not have to use XI methods. So what they told me is some of the research in physics and physics connected to machine learning is kind of going back to other things like not using deep neural networks, but using physics-informed decision trees and so on to kind of get an understanding without using or having to use XI methods. Because, of course, it is a bit problematic even with this ADO method, because you have to have at least some understanding of the physics to kind of extract information. Just even these EFPs, while they are kind of on the descriptive side, have to be kind of known to use them. Yeah.
Okay, thanks.
Thanks. Any other questions? I'll take the opportunity to ask one then while other people are thinking if they have any. I wanted to take issue, it's not really so much with you, but with the definition of intelligibility that you used. Could you maybe pop back to that slide? I think it's is it Gebers? I pronounce the name hard to pronounce. He works with direct. That's his definition. Yeah, it's actually it's direct. I thought it might be no joint paper. So my concern with this definition is that I tend to think that intelligibility is actually a matter of degree. It's not a binary on-off thing. So if you compare two models, imagine we have two models that will both predict exactly the same thing, but one is super complex and you need to actually maybe run it through a supercomputer to get those predictions, whereas the other one can do like pen and paper, a human being. It seems to me that you could, and I imagine that both of them, you can recognize something qualitatively characteristic in both cases, right? So even the one you have to put through the supercomputer, you can still recognize something qualitatively characteristic. And they're just a very limited set of consequences, whereas the other one, you can just see so many different kinds of consequences in different contexts. It seems to me that the model that's a pen and paper model is more intelligible than the other model, although they're predictably both the same. And this definition of intelligibility makes it kind of very easy to achieve intelligibility with actually a really complex and ugly model, because it's just got one kind of qualitatively characteristic set of consequences. So I don't know what you think about that.
Yeah, I think even though it's kind of not explicitly in this definition, it is kind of what's being meant, because in the context of what I talked about with this string model or other phenomenological models, the Recht talks about kind of you can get the same predictions you get from the string model by using numerical methods, but nobody understands them, and you do not get those qualitative characteristic consequences. So I think it is implicit that there is a degree of intelligibility. So you get some kind of understanding from the numerical method, but with the string model or other models, you get more qualitatively characteristic consequences without having to perform calculations.
Okay,
Does that answer your question?
Yeah, it's been a long time since I read him. So, but the example you gave seems to be one where he was saying there was nothing from the numerical methods at all, and then all of a sudden you had it in the other case. Yeah.
Yeah, so I think it's a bit better in the Hartmann paper, which I kind of cited, because he does a really better, like a really in-depth analysis of this, and he's talking a lot more about the numerical method. But I take it that both of them kind of say there's not a lot we gain from this, like not a lot of understanding.
Yeah, yeah. I guess I'd just say it's partially intelligible for scientists.
Yeah.
But then you have to relativize intelligibility to yeah, I mean, really what you want to do is you want to relativize intelligibility to all the predictive capacities of the model. That's the correct way to do it, isn't it? So
Yeah.
the intelligible a model can be is if you can understand all the relatively qualitatively characteristic consequences that relate to what the model can do completely predict. For that particular model. That can vary too, of course. Different models have different predictive capacities, but the intelligibility should be relativized to the predictive capacities of the model.
Yeah, that makes a lot of sense. Yeah.
Yeah. I just wanted to work it out in my own head, so when I write about this, I get it right. Okay. The other Junotsuka has a question.
Hi, I'm Jun from Kyoto University. Well, thank you very much for your talk. I really like your way of describing XAI and representation learning as a kind of tools to kind of tackle intelligibility of machine learning outcomes. But I also see that there are kind of challenges. So, for example, XAI is kind of mostly a kind of linear approximation. So it's kind of known to, decrease the predictive power of machines or AI or deep learning models. And also in the representation learning, well, representation machines built are usually incomprehensible to us. So it's so complex that it's very difficult to kind of identify the representation that we can understand. So how I'm curious about your thought on these kind of the challenges of your proposal.
Yeah, thanks for the question. I feel like those methods I presented are kind of a bit about interpreting. So in a sense, so for example, the data planning case, when they removed the mass information from the data and then found out that the neural network didn't work anymore. From our point of view, of course, we could now say, okay, the DNN kind of, in some sense, had a representation of this mass information. But when we think about it, this does not really have to be true. It could have used kind of different things that for us kind of make up what we take to be mass. So I think what those methods do is they kind of do not explicitly care whether this is exactly the variable represented in the neural network, but we can take it to be represented in the network. I hope I'm explaining this well enough. But so I think, and this is the problem with these methods, that you have to have a lot of kind of interpretive capabilities. You kind of have to have some sort of understanding or some sort of knowledge about the target system to use those methods, because you take a lot of interpretation onto the system. While of course it could be that the network didn't use the mask, it used some kind of other, because the mask is kind of is a high level variable, so it's kind of based on many low level variables. And it could be that those are kind of differently packed into the network, but for us, it looks like it uses the mask. So I feel like those methods kind of just skip this step and kind of just say, let's just interpret it the way we can do it. I hope this answers your question.
Oh, great. Well, thanks. It's interesting. So you treat kind of machine learning models as a kind of phenomena by themselves, and use XAI and representation as a kind of, we study these phenomena, machines, with XAI and representation. Is that you are suggesting, if I understand correctly? Maybe.
Let me just think about it. In a sense, I think yes. So the only point I kind of want to make about this is that we just kind of take the neural network to represent something. And it isn't really important if it really does represent it in the way we kind of think or interpret it to do, but we take it kind of to represent. So there's this interpretive step. So yeah, I think if that's what you meant with your kind of a sentence right now, then yeah, that's what I wanted to say.
Okay, well, thank you very much.
Yeah, isn't it the input-output relationship that you're really looking at? So you're using the input-output relationship, and then you're doing an interpretation of what causes that. Is that all right?
Yeah.
Yeah, that fits my own view of how it works. That fits my own view of understanding in this context. Yeah, good.
Great.
Any more questions? Okay, thanks again for giving the talk. It's still very early over there. Maybe you'll be going back to bed or maybe having breakfast.
Yeah, maybe.
Thanks very much for coming along virtually anyway. Sorry you couldn't make it in person.
Yeah, thanks for having me, and thanks for the interesting discussion, and have a lot of fun.
Great. Yeah, thank you. Bye-bye.
Bye.